Welcome to this problem walkthrough. Today, we'll explore LeetCode problem number 975, titled Odd Even Jump. This is a fascinating challenge that combines array traversal with dynamic programming, and we'll discuss how to approach it step by step. Let's dive in. In this problem, we are given an integer array called ARR with a length of n. Our goal is to figure out how many indices in this array can be considered good starting points. An index I is called good if, starting from that index, we can reach the end of the array by following a specific jumping pattern. The jumping pattern alternates between odd and even jumps, beginning with an odd jump. Now, during an odd jump, we move from the current index I to a new index j, where j is the smallest index greater than I such that the value at ARR, j, is at least as large as the value at ARR, I. If there are multiple valid options for j, we pick the smallest one. On the other hand, during an even jump, we move to the smallest index j greater than I where the value at ARR, j, is less than or equal to the value at ARR, I. Again, we choose the smallest possible j if there are ties. If no valid j exists during either an odd or even jump, the process stops, and we cannot reach the end of the array from that starting index. Our goal is to return the total number of good starting points in the array. The output for this problem is a single integer, which represents the count of good starting indices in the array. Let's look at an example to better understand the rules and the approach. Suppose the input array is 10, 13, 12, 14, 15. The output for this array is 2. Why? From index 1, 0 based, we start with an odd jump. The value at index 1 is 10, and the next smallest index where the value is greater than or equal to 10 is index 2, which has the value 13. Then, we perform an even jump. From index 2, the value is 13, and the smallest index where the value is less than or equal to 13 is index 3, which has the value 14. Finally, we perform another odd jump from index 3 to index 4 because the value at 4 is 15, which is greater than or equal to 14. At this point, we have reached the end of the array. Therefore, index 1 is a good starting point. Now consider index 3. Starting from index 3, the value is 14. For the first jump, which is an odd jump, we move to index 4, where the value is 15. Since we have now reached the end of the array, index 3 is also a good starting point. This means that for the array 10, 13, 12, 14, 15, the good starting indices are 1 and 3. So the output is 2. Let's examine another example. If the input array is 2, 3, 1, 1, 4, the output is 3. Starting from index 0, the value is 2. For the first jump, we perform an odd jump to index 1, where the value is 3. Then, we perform an even jump to index 4, where the value is 4. At this point, we have reached the end of the array, making index 0 a good starting point. Next, let's look at index 2 in the same array, 2, 3, 1, 1, 4. Starting from index 2, the value is 1. For the first jump, which is an odd jump, we move to index 4 because that's the smallest index where the value is greater than or equal to 1. Since index 4 is the end of the array, index 2 is also a good starting point. Finally, consider index 4. Since index 4 is already the last index of the array, it is trivially a good starting point. In this example, the good starting indices are 0, 2, and 4, so the output is 3. Now let's analyze another example. If the input array is 5, 1, 3, 4, 2, the output is 2. For the array 5, 1, 3, 4, 2, start with index 3, where the value is 4. The first jump is an odd jump, which moves us to index 0 because the value at index 0 is 5, which is greater than or equal to 4. Since index 0 is the end of the array, index 3 is a good starting point. Now consider index 4, where the value is 2. Since index 4 is already the last index, it is a good starting point by default. Thus, the good starting indices for this array are 3 and 4, giving an output of 2. As we wrap up, remember that the constraints of the problem ensure that the input array has a length between 1 and 20,000. Special cases to note include arrays with only one element, where the only index is always a good starting point. For arrays with all identical elements, every index is valid because the jumps will always find the next index. Finally, if the array is sorted, either odd or even jumps will consistently succeed, depending on the order of the sorting. To tackle the odd-even jump problem, we start by considering different approaches. The most intuitive way is the brute force method. Here, we simulate the jumps for every index in the array by directly following the rules. For an odd jump, we look for the smallest index greater than the current one, where the value at that index is at least as large as the current value. For an even jump, we look for the largest index greater than the current one, where the value at that index is at most the current value. While this approach is conceptually simple, it involves scanning the array repeatedly to find valid jumps. With n indices and up to n steps per index, this results in a time complexity of O(n squared). Next, we consider optimizing this process using sorted maps, such as TreeMap in Java or sorted dict in Python. These data structures allow us to dynamically track elements and efficiently retrieve the next smallest or largest index needed for odd and even jumps. This reduces the overhead of scanning the array, bringing the complexity down to O(n log n). However, maintaining sorted maps still incurs logarithmic costs, leaving room for further improvement. A more efficient approach uses monotonic stacks to pre-process the indices required for odd and even jumps. The idea is to sort the array by values, and in the case of ties, by indices. For odd jumps, we use ascending order, while for even jumps, we sort in descending order. Once sorted, we use a stack to determine the next valid jump indices for each position. This pre-processing step is key, as it eliminates the need for repeated scans of the array. After we have the next valid indices, we use dynamic programming to determine whether each index is a good starting point. We define two Boolean arrays, odd and even. The odd array tracks if we can reach the end starting with an odd jump, while the even array tracks the same for even jumps. The transitions are straightforward. If the next odd jump from index I leads to an index marked as true in the even array, then odd I is true. Similarly, if the next even jump leads to an index marked as true in the odd array, then even I is true. Finally, summing up the true values in the odd array gives the total number of good starting indices. The core insight that simplifies this problem is realizing that the next jump indices can be pre-computed efficiently using sorting and a monotonic stack. This eliminates the need for repeated scans, reducing the overall complexity from O(n squared to O(n log n). The monotonic stack approach is particularly appealing because it balances efficiency with simplicity. Sorting the array and using stacks for pre-processing is intuitive to implement and scales effectively for large inputs. Comparatively, the brute force method is impractical due to its quadratic complexity, and while sorted maps offer an improvement, they introduce unnecessary overhead. In contrast, the monotonic stack approach is optimal in both time complexity and clarity. This makes it the best choice for solving this problem, as it provides a robust solution that is both scalable and easy to understand. In this problem, we are given an array of integers called ARR, and our goal is to determine how many indices are considered good. A good index is one from which we can start and eventually reach the end of the array by following a specific set of jumping rules. These jumps alternate between odd and even jumps. An odd jump is defined as moving to the smallest index j greater than the current index I such that the value at ARR j is greater than or equal to ARR I. If there are multiple such indices, we choose the smallest one. On the other hand, an even jump moves to the smallest index j greater than I such that ARR j is less than or equal to ARR I. Again, if multiple indices qualify, the smallest is chosen. Our task is to calculate the total number of indices that can eventually lead to the end of the array by alternately following these rules for odd and even jumps. To solve this problem, one way is to use a brute force approach. Here, we simulate the jumping process for every index I in the array. We begin by initializing some key variables. Let n be the length of the array, and set good_indices_count to 0, which will keep track of the total number of good indices. For each index I in the array, we simulate the jumps starting from that index. The jumps alternate between odd and even, and the simulation continues until either we reach the last index, at which point we count I as a good index, or we fail to find a valid jump. For odd jumps, we look for the smallest index j greater than I such that ARR j is greater than or equal to ARR I. For even jumps, we find the smallest index j greater than I such that ARR j is less than or equal to ARR I. This process is repeated for every index to determine if it qualifies as a good index. After simulating the jumps for each index, if we find that starting from a particular index I allows us to successfully reach the last index, we increment the good indices count. Once we complete the simulation for all indices in the array, we return good indices count as the total number of good indices. However, this approach is computationally expensive. Finding the next valid jump for a single index requires scanning through the array, which has a time complexity of O(n). When we simulate this for all indices, the overall time complexity becomes O(n squared) in the worst case. This inefficiency highlights the need for optimization, especially for larger input sizes. To improve efficiency, we use an optimized approach that combines dynamic programming with monotonic stacks. The brute force method is slow because it repeatedly scans the array to find the next valid jump. Instead, we pre-compute these jumps in advance. First, we initialize key data structures. Two Boolean arrays can_each_odd and can_reach_even, both of size n, are set to false initially. These arrays will store whether each index can eventually reach the end using odd or even jumps, respectively. We know that the last index of the array is always a good index, so we set both can_reach_odd, n1, and can_reach_even, n1, to true. Next, we pre-compute the next valid odd and even jumps using a monotonic stack. To find the next odd jump for each index, we sort the indices of the array based on their values in ascending order. Similarly, for even jumps, we sort the indices in descending order. The monotonic stack allows us to efficiently compute the next valid index for each jump. Once we have pre-computed the next valid odd and even jumps, we use dynamic programming to calculate whether each index can reach the end. Starting from the second to last index and moving backward, we update the can_reach_odd and can_reach_even arrays based on the pre-computed jumps. For an odd jump at index I, if the next odd jump leads to an index where can_reach_even is true, we set can_reach_odd, I, to true. Similarly, for an even jump at index I, if the next even jump leads to an index where can_reach_odd is true, we set can_reach_even, I, to true. After processing all indices, we count the number of indices where can_reach_odd is true, as these are the good indices. The final result is this count. The time complexity of this approach is much improved. Sorting the indices takes O(n log n), and the monotonic stack operations, along with dynamic programming transitions, take O(n). This gives us an overall complexity of O(n log n). There are several key insights that make this optimized approach efficient. First, sorting the indices by their values enables us to use a greedy strategy for selecting the next valid jump. By leveraging a monotonic stack, we can find the next higher or lower index in constant time for each index after sorting. Second, dynamic programming allows us to store intermediate results in the can_reach_odd and can_reach_even arrays. This avoids redundant computations, as we only calculate each result once and reuse it. Finally, the use of specific data structures like monotonic stacks and sorted index lists ensures that our solution remains both space-efficient and time-efficient. Together, these insights enable us to solve the problem optimally. Lastly, it's important to consider edge cases to ensure our solution works for all scenarios. For example, in an array with a single element, that index is always a good index since no jumps are required. If all elements in the array are equal, any index can jump to the next one, making all indices good. In strictly increasing or decreasing arrays, only odd or even jumps will be valid, depending on the direction. Our optimized approach handles these edge cases effectively due to its systematic pre-computation and dynamic programming framework. By considering these scenarios, we can confidently conclude that our solution is robust and efficient across all inputs. Here, we start by importing the sortedDict class from the sorted containers module, which helps us efficiently manage and retrieve indices in sorted order. The solution class defines the function odd-even-jumps, which takes an array, ARR, as input. First, we calculate the length of the array n. If the array has only one element, we directly return 1 because there's no jumping involved. Next, we initialize two Boolean arrays, odd_jump_good and even_jump_good, both of size n. These arrays will track whether it's possible to reach the end of the array starting from each index using odd jumps and even jumps respectively. We set the last index of both arrays to true because reaching the end from the last index is trivially possible. We then initialize a sorted dict called sorted_map to store elements of the array along with their indices. This data structure allows us to efficiently find the next smallest or largest index for odd and even jumps. Initially, we populated with the last element of the array and its index. Now, for each index in reverse order, starting from the second to last index, we determine the next index for an odd jump using the bisect_left method. If a valid candidate exists, we update the odd_jump_good array at the current index based on the even_jump_good value at the candidate's index. This ensures that an odd jump from the current index leads to a valid path. For the even jump, we use the bisect_right method of the sorted_map to locate the next smaller or equal value. We adjust the candidate index by subtracting 1 to ensure we're looking at the largest valid candidate smaller than or equal to the current value. If such a candidate exists, we update the even_jump_good array at the current index based on the odd_jump_good value at the candidate's index. This ensures that an even jump from the current index leads to a valid path. After processing both odd and even jumps for the current index, we update the sorted_map with the current element and its index, ensuring that it remains accurate for subsequent iterations. Finally, to determine the result, we count all the indices in the odd_jump_good array that are marked true. These represent the starting indices from which we can reach the end of the array using valid odd jumps. The function then returns this count as the result. Here, we begin the implementation of the odd-even jumps solution in Java. First, we import the necessary packages, and then we define the main method within the solution class. The method takes an integer array ARR as input, representing the given sequence of integers. We start by determining the length of the array, n. If the array contains only one element, we immediately return 1, since a single element is trivially reachable. Next, we declare two Boolean arrays, odd_jump_good and even_jump_good, both of size n. These arrays will help us track whether we can reach the end of the array starting from each index using an odd or even jump, respectively. For the last element of the array, both jumps are trivially valid, so we set the corresponding values in these arrays to true. We then initialize a tree map called sorted_map, which will be used to efficiently find the next higher or lower value for odd and even jumps. Initially, we add the last element of the array to this map, associating its value with its index. Now, we iterate backward through the array, starting from the second to last element. For each index, we handle odd jumps first by finding the smallest key in the map that is greater than or equal to the current array value using the ceiling entry method. If such a key exists, we update the odd_jump_good array for the current index based on the corresponding value in the even_jump_good array for the destination index. Similarly, for even jumps, we use the floor entry method to find the largest key that is less than or equal to the current value, and if found, we update the even_jump_good array for the current index based on the corresponding value in the odd_jump_good array for the destination index. After processing both odd and even jumps for the current index, we update the sorted map with the current array value and its index to ensure it's available for future iterations. Once the loop completes, we compute the result by iterating through the odd_jump_good array. For each index, if the value is true, it means starting from that index with an odd jump sequence allows us to reach the end of the array. We increment our count for each of these valid indices. Finally, we return the count, which represents the total number of starting indices from which we can reach the end of the array using the odd-even jump rules. This completes the implementation of the solution in Java. Here, we start analyzing the input array 10, 13, 12, 14, 15. We initialize n to 5 since there are 5 elements in the array. The odd_jump_good and even_jump_good arrays are initialized with false values for all indices except the last one, which is true, as the last position is always reachable. The sorted_map begins with 15, 4, representing the last element and its index. For iteration 1, where I equals 3 and the value is 14, we determine the next larger value using bisect_left, finding 15 at index 4. Since even underscore jump underscore good, 4, is true, we update odd underscore jump underscore good, 3, to true. For the even jump, bisect underscore right, 14, 1 shows no smaller value exists, so even underscore jump underscore good, 3, remains false. After updating sorted underscore map to include 14, it becomes 14, 3, 15, 4. Now, for iteration 2 where I equals 2 and the value is 12, we again use bisect underscore left to find the next larger value, which is 14 at index 3. Since even underscore jump underscore good, 3, is false, odd underscore jump underscore good, 2, remains false. For the even jump, bisect underscore right, 12, 1 reveals no smaller value exists, so even underscore jump underscore good, 2, stays false. The sorted underscore map is updated to include the current value, resulting in 12, 2, 14, 3, 15, 4. Moving to iteration 3, for I equals 1 and the value 13, the next larger value found with bisect underscore left is 14 at index 3. Again, since even underscore jump underscore good, 3, is false, odd underscore jump underscore good, 1, remains false. For the even jump, bisect underscore right, 13, 1 finds 12 at index 2. Since odd underscore jump underscore good, 2, is also false, even underscore jump underscore good, 1, is updated to false. The sorted underscore map becomes 12, 2, 13, 1, 14, 3, 15, 4. For the final iteration, I equals 0 and the value is 10. Using bisect underscore left, the next larger value is 12 at index 2. Since even underscore jump underscore good, 2, is false, odd underscore jump underscore good, 0, remains false. For the even jump, bisect underscore right, 10, 1 shows no smaller value exists, so even underscore jump underscore good, 0, stays false. After adding 10 to the sorted underscore map, it becomes 10 o'clock, 12, 2, 13, 1, 14, 3, 15, 4. At the end of this process, the odd underscore jump underscore good array is false, 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 true, true, and even underscore jump underscore good is false, 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 true. The number of true values in odd underscore jump underscore good gives the result, which is 2. In this second example, the input is 2, 3, 1, 1, 4. As before, we initialize end of 5, odd underscore jump underscore good and even underscore jump underscore good with all false except the last index, and sorted underscore map as 4, 4. For iteration 1, where I equals 3 and the value is 1, bisect underscore left finds the next larger value is 4 at index 4. Since even underscore jump underscore good, 4, is true, we set odd underscore jump underscore good, 3, to true. For the even jump, bisect underscore right, 1, 1 shows no smaller value exists, so even underscore jump underscore good, 3, remains false. The sorted underscore map is updated to 1, 3, 4, 4. In iteration 2, I equals 2 and the value is 1. Using bisect underscore left, the next larger value is found at index 3. Since even underscore jump underscore good, 3, is false, odd underscore jump underscore good, 2, remains false. Similarly, bisect underscore right, 1, 1 shows no smaller value exists, so even underscore jump underscore good, 2, stays false. The sorted underscore map becomes 1, 2, 4, 4. For iteration 3, where I equals 1 and the value is 3, bisect underscore left finds the next larger value is 4 at index 4. Since even underscore jump underscore good, 4, is true, odd underscore jump underscore good, 1, is set to true. For the even jump, bisect underscore right, 3, 1 returns 1 at index 2. Since odd underscore jump underscore good, 2, is false, even underscore jump underscore good, 1, remains false. The sorted underscore map updates to 1, 2, 3, 1, 4, 4. Finally, for iteration 4 where I equals 0 and the value is 2, bisect underscore left finds the next larger value is 3 at index 1. Since even underscore jump underscore good, 1, is false, odd underscore jump underscore good, 0, remains false. For the even jump, bisect underscore right, 2, 1 returns 1 at index 2. Since odd underscore jump underscore good, 2, is also false, even underscore jump underscore good, 0, stays false. The sorted underscore map updates to 1, 2, 2 o'clock, 3, 1, 4, 4. At the end, the odd_jump_good array is false, true, false, true, true, and even_jump_good is false, 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 true. Summing the true values in odd_jump_good gives the output, which is 3. Here, we analyze the third input array, 5, 1, 3, 4, 2. We then set to 5 and odd_jump_good and even_jump_good initialized as before. The sorted underscore map starts as 2, 4. For iteration 1, I equals 3 and the value is 4. Using bisect_left, no larger value is found, so odd_jump_good, 3, remains false. For the even jump, bisect_right, 4, 1 returns 2 at index 4. Since odd_jump_good, 4, is true, even_jump_good, 3, is updated to true. The sorted underscore map becomes 2, 4, 4, 3. In iteration 2, I equals 2 and the value is 3. Using bisect_left, the next larger value is 4 at index 3. Since even_jump_good, 3, is true, odd_jump_good, 2, is also set to true. For the even jump, bisect_right, 3, 1 returns 2 at index 4. Since odd_jump_good, 4, is true, even_jump_good, 2, is updated to true. The sorted underscore map is updated to 2, 4, 3, 2, 4, 3. For iteration 3, I equals 1 and the value is 1. Using bisect_left, the next larger value is 2 at index 4. Since even_jump_good, 4, is true, odd_jump_good, 1, is updated to true. For the even jump, bisect_right, 1, 1 finds no smaller value, so even_jump_good, 1, remains false. The sorted underscore map becomes 1, 1, 2, 4, 3, 2, 4, 3. For iteration 4, I equals 0 and the value is 5, no larger value is found with bisect_left. So odd_jump_good, 0, stays false. For the even jump, bisect_right, 5, 1 finds 4 at index 3. Since odd_jump_good, 3, is false, even_jump_good, 0, remains false. The sorted underscore map updates to 1, 1, 2, 4, 3, 2, 4, 3, 5 o'clock. At the end of this example, the odd_jump_good array is false, true, true, false, true, and even_jump_good is false, false, true, true, true. The number of true values in odd_jump_good is 3, which is the output for this input. To analyze the time complexity of the odd-even jump algorithm, let's break it down step by step. First, initializing the odd_jump_good and even_jump_good arrays, each of size n, is straightforward and takes n time. Next, we use a sorted dict to efficiently find the next valid jump indices for both odd and even jumps. The key operations here include bisect_left and bisect_right, which help locate the smallest and largest keys relative to the current value. These operations each take log n, due to the efficient binary search mechanism of the sorted dict. Additionally, accessing an element using peak_item is 1, and updating the sorted dict, whether by adding or modifying an entry, also takes log n. Lastly, the outer loop iterates from the second to last index to the first index, making n iterations in total. Each of these components contributes to the overall time complexity, which we'll examine further. Now, within each iteration of the loop, several operations are performed. First, 2 bisect operations are executed, one for odd jumps and one for even jumps, and since each takes log n, this contributes 2 log n, which simplifies to log n. Additionally, we perform 2 peak_item operations, which are 1 each, but their contribution is negligible in comparison. Updating the sorted dict is another key operation and takes log n. Since these operations are repeated for every iteration, and the loop itself runs n times, the total time complexity becomes n multiplied by log n, resulting in n log n. Importantly, this time complexity is consistent across the best, average, and worst cases, as it depends only on the size of the input array n and the efficiency of binary search operations in the sorted dict. Next, let's consider the space complexity of the algorithm. The two Boolean arrays, odd_jump_good and even_jump_good, have a size proportional to the input array, contributing O(n) space. The sorted dict also plays a role in the space complexity. In the worst case, the sorted dict could store all n elements from the input array, which adds another O(n). Combining these, the total space complexity becomes O(n) for the arrays and O(n) for the sorted dict, resulting in an overall space complexity of O(n). Additional storage for variables and intermediate computations is negligible in comparison, so it doesn't impact the final analysis. To further understand the efficiency of the optimized approach, let's compare it with a brute force solution. In a naive method, we would compute all possible odd and even jumps for every index. This involves iterating through the remaining indices for each jump, which takes O(n) time per index, resulting in a total time complexity of O(n squared). This is significantly slower than the optimized solution. By leveraging the sorted dict for dynamic sorting and efficient binary search, the optimized approach reduces redundant computations and achieves a time complexity of O(n log n). This improvement is a direct result of combining the dynamic properties of the sorted dict with the linear traversal of the array, making the algorithm much more scalable for large inputs. Finally, let's mathematically confirm the big O complexity. The dominant factor in time complexity is the combination of the loop and the sorted dict operations. The loop runs O(n) times, and within each iteration, binary search and updates in the sorted dict take O log n. When these are multiplied, the total time complexity becomes O(n) asterisk O log n, which simplifies to O(n log n). For the space complexity, we see that the sorted dict and the Boolean arrays each grow linearly with the size of the input. Adding these together gives O(n) space usage overall. This mathematical breakdown verifies that the algorithm is both time efficient and space efficient, especially when compared to less optimized approaches. When tackling the odd-even jump problem, there are a few common mistakes that candidates often run into. First, it's crucial to correctly alternate between odd and even jumps. Starting with an odd jump from each index, the sequence must strictly alternate odd, even, odd, and so on. Confusing this order can lead to completely incorrect traversal logic, causing the algorithm to fail. Another frequent issue is relying on an inefficient brute force implementation. Calculating all possible jumps from each index without optimization can result in a time complexity of O(n squared asterisk log n, which is far too slow for larger input sizes and won't scale well. Boundary case errors are another pitfall. For example, arrays with only one element or with repeated elements can cause unexpected behavior or runtime errors if not explicitly handled. Lastly, be mindful of using the right data structures. Naively sorting the array repeatedly or using inefficient structures can drastically increase the time complexity. Balanced binary search trees, or similar data structures, are much better suited for maintaining sorted order efficiently while performing lookups. Another mistake to avoid is overlooking space complexity. Remember that the auxiliary data structures you use can consume significant memory, especially for large inputs. Excessive memory usage can lead to overflows in constrained environments, so it's important to strike a balance between time and space efficiency. During interviews, this problem is often used to test your ability to recognize patterns, such as jumping behaviors, sorting requirements, and dynamic programming principles. Interviewers typically expect you to start with a brute force approach to show your understanding of the problem, but you should quickly pivot to optimized solutions by leveraging pre-computation or efficient lookups. Communication is also key. Make sure to clearly explain how the odd and even jumps alternate, and highlight how you handle edge cases. Finally, it's important to address time complexity trade-offs. While brute force may suffice for small constraints, you should emphasize that an O(n asterisk log en solution is necessary for scaling to larger inputs, demonstrating your optimization mindset. The odd-even jump problem also shares similarities with several related problems, which can help you build intuition and transferable skills. For instance, LeetCode 42, Trapping Rainwater, emphasizes the use of indices and pre-computed values, which is a recurring theme here. LeetCode 496, Next Greater Element I, involves efficient lookups for the next valid index, something you'll need to master for odd and even jumps. LeetCode 239, Sliding Window Maximum, is another example where optimized data structures are used to handle range queries efficiently. Finally, LeetCode 321, create maximum number, combines sorting and dynamic programming logic, which is highly relevant to this problem. Exploring these problems can deepen your understanding of the patterns involved. Now, alternative approaches to solving odd-even jump include dynamic programming with a sorted map. This method uses a data structure like a tree map to efficiently find the next smallest or largest index during jumps. While this reduces the time complexity to O and log n, it does come with the trade-off of requiring additional space for the map. Another alternative approach is using a monotonic stack. With this method, you can pre-compute the next valid indices for both odd and even jumps, leveraging the stack's properties to optimize these calculations. This approach tends to be more space efficient, but it does require careful implementation to ensure that the stack operations maintain correctness. Finally, there's the option of reverse dynamic programming. Instead of working forward from the start of the array, this approach involves pre-computing reachable indices by working backward from the end. While this can simplify certain aspects of the implementation, it may feel less intuitive for some candidates to explain in an interview setting. Each of these alternative strategies comes with its own trade-offs, so understanding their strengths and weaknesses is key to selecting the best approach for the given constraints. Great job completing the odd-even jump walkthrough. We've summarized the key points, including the algorithm, time and space complexities, and the big takeaways. I hope you found this tutorial helpful and engaging. Don't forget to like and subscribe for more coding content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!